or now we can start. Hello, everyone, and welcome back to another session of the Discovery Seminar Talks. My name is Ramona Augustine. I'm a Space Telescope postdoc working with Molly Peoples and Jason Tomlinson, and I will be hosting today's session. For those of you who join us for the first time today, the aim of this talk series is to showcase the work of postdocs at Space Telescope and the Johns Hopkins University. Because, as you surely all know, early career researchers have been disproportionately impacted by the COVID-19 pandemic due to reduced travel and networking opportunities. With this talk series that is currently scheduled until the end of July, we want to provide a platform for postdocs to show their results to an international audience of astronomers. Today we will have two talks, 20 to 25 minutes each. At the end of each talk, please feel free to ask questions to the speakers. For that, you can use the raise hand button, and then I will call your name and you can unmute yourself and speak. Or if you feel more comfortable, you can also put the question into the chat and I can read it for you. So today's first speaker is Darshan Kakkad. Darshan got his PhD from Ludwig Maximilians University in Munich in 2017, where he worked on ionized and molecular gas kinematics of low redshift and high redshift galaxies to understand feedback from the central supermassive black holes. After that, he moved to the European Southern Observatory in Chile as an ESO fellow, where for half of his time he conducted an independent research program on the characterization of outflows and ISM conditions in galaxies. The other half of his time, he supported science operations at the VLT as a MUSE instrument fellow. For his fourth year of the fellowship, he moved to Oxford University to work with the Harmony ELT team on improving sky subtraction techniques with current and future IFS instruments from ground-based telescopes. And since early this year, he has been an STScI fellow working with the COS team and conducting research on outflow launching mechanisms, AGN feedback, and star formation histories in galaxies across a wide range of redshifts. Today, he will tell us about his work on AGN-driven outflows and their impact on star formation across cosmic time. Darshan, the floor is yours.
Thanks a lot, Ramona. Let me share my screen. Can you see my slides? Perfect. And you can hear me well as well. Great. Okay, so thanks, Ramona. For those of you who don't know me, I'm Darshan Kakkad. I'm an STScI fellow here at Space Telescope Science Institute. And today I will give you a very general overview of what I have been involved with or what I have been doing from the research point of view. Primarily, I'll talk about outflows in AGN host galaxies and how these outflows may impact star formation. And I've said across cosmic time, but then the impact of star formation is something that I'll focus mostly for the high redshift galaxies. So the modern galaxy formation theory is set within the larger scale CDM cosmological model. Within this paradigm, the formation of structure within the universe is seeded by minute perturbations in matter density, which are then expanded to cosmological scales by inflation. The dark matter component undergoes gravitational collapse, ultimately leading to the formation of a dark matter halo, which is a near equilibrium state, which is supported against its own self-gravity. Galaxies form within these deep halos of the dark matter halos, and in a hierarchical universe, these halos merge to form larger structures, and these structures are then connected by these filaments as shown in this plot. And as you start zooming in, you start looking at what I would call as familiar-looking galaxies, and what I'll say as almost real-looking galaxies as well. And so I feel that the simulations are doing a very splendid job these days in almost creating a real-looking universe, perhaps partly thanks also to the plethora of information that we have gained from observations themselves. So if we just assume this lambda CDM cosmology and let the galaxies grow as they are, and then plot the galaxy luminosity functions, compare them with observations, this is what we obtain. We immediately realize that we are over-predicting the number of galaxies at the two ends of the luminosity function. The reason for this is that there is no mechanism in place that is able to regulate the flow of gas into these galaxies. So due to this, the galaxies are just weighed down in mass. So in order to control this, several kinds of feedback need to be incorporated that will allow the luminosity function from simulation to reconcile with those which is observed in the literature. So at the low mass end, we invoke a supernovae-driven feedback or starburst-driven feedback or so to bring down the number of observed low luminosity galaxies. And while at the high mass end, a more powerful process such as black hole feedback or AGN feedback needs to be invoked. Another way of looking at this is that in both of these cases, the supernovae-driven feedback and AGN feedback just basically bring down the efficiency of star formation at these two low mass as well as the high mass ends. So how would such a feedback process work? So here I'm just giving you a very toy model of what an AGN feedback might look like and how it affects the gas flow within the host galaxies. So let's start with a galactic disk with a very beautiful black hole in the center. And these galactic disks may contain molecular gas clouds. And these molecular gas clouds can eventually give rise to the formation of stars. And the gas and dust within the host galaxy can also feed the black hole in the center. And as a process of as a result of this feeding, there's radiative feedback that can happen through which the radiation pressure-driven winds are swept across the host galaxy, removing the molecular gas. And without this molecular gas, the star formation will eventually quench in these host galaxies, leading to the formation of a red and dead passive galaxy. Now, as I said, that this is a toy model. This is very simplistic, but it gives you an idea of how it works. So the main open questions within this topic is that we first want to know what drives these outflows, whether it's the AGN itself or whether there's starburst or nuclear star formation and so on. How efficiently does this coupling take place between the outflow and the ISM? And lastly, how exactly can we design an experiment that will allow us to infer a direct evidence of AGN feedback in action? That means that whether we can see outflows actively quenching star formation or not. So before going further, I should mention that AGN feedback is only one of the processes through which the star formation is quenched within the host galaxy. This slide sort of gives you a quick look into many different quenching mechanisms. So the first of which could be, say, in an isolated galaxy, where most of the gas is lost via Raman pressure stripping. And without any interactions with another galaxy, this galaxy would just consume all of its gas, depriving the stars within this galaxy of the fuel, which is the molecular gas. And metallicity measurements of some isolated galaxies have actually shed light on how this process may work. The other process, which is the starburst-driven quenching mechanism, which is very similar to black hole-driven mechanism that I just mentioned a slide back, except that in this case, high amounts of star formation is the one which is causing the outflows and then removal of the gas supply. And lastly, we have the gravitational shock heating as well in massive halos, which can also lead to the star formation quenching in these host galaxies. But for the purpose of this talk, I will mostly focus on outflows from AGN as a mechanism of quenching. So what we'll do is we'll characterize what outflows look like, how fast are the outflows, how much of mass is there within these outflows, and consequently, how much of kinetic power will be there within these winds. So the actual AGN outflow would probably look somewhat like that. So moving a step further from the simplistic model that I mentioned earlier. So in this case, you would have like different level of shock media, and depending on whether the outflow is momentum driven or energy driven, the outflow can propagate to different scales of the host galaxy. So in both of these cases, we start with a wind that impacts against the ISM of the host galaxy, producing a shock wave front. So this produces an inverse reverse shock, slowing down this wind, but it also produces an outward forward shock, which accelerates the gas. And in the momentum-driven case, which happens in case of, say, very fast outflows, the shocks are very narrow and they rapidly cool to become effectively isothermal. So in this case, most of the kinetic energy is lost to the radiation, and the coupling with the ISM is not as strong. In the energy-driven outflow, in the other case, on the other hand, the shock regions are much wider, and they don't cool, and they expand adiabatically, and as a result, communicates most of the kinetic energy of the wind of the outflow to the ISM. And in this case, the gas is able to go down up to kiloparsec scales, which is what we see in a lot of galaxies. So, obviously, from our previous plot, we know one thing for sure, that the outflows driven by AGN are a multi-scale phenomenon. So depending on which kind of an outflow is driven, how fast it is, we can observe outflows which are very close to the AGN location, so sub-parsec scales, from parsec scales to kiloparsec scales, or basically sub-parsec scales, and to tens of kiloparsec scales or so. This is also, so the outflows being driven to very large scales is also used to explain the high fraction of metals that is often observed in the outskirts of the galaxy. So for the purpose of this talk, I will focus on these two aspects of the outflow, that is the sub-kiloparsec scales to kiloparsec scales. So I won't really be talking much about the outflow which is originating very close to the AGN location. So in addition to the multi-scale phenomenon, outflows are also multi-phase, meaning that outflows can exist in multiple phases like ionized gas phase, molecular, neutral, and even within molecular you would have the cold molecular gas and warm molecular gas and so on and so forth. So as an example, in this image, the background image shows the ionized gas outflow. In the red, you can see the molecular gas, and in white, cold molecular gas in red, and in white, you can see the warm molecular gas. And you can clearly see that each of these phases traces a different region in the host galaxy. So observations in these different wave bands are just complementary to each other. What remains to be seen is which phase is dominant, and whether this dominance of the phases, whether the cold molecular gas phase or ionized gas phase, which one dominates, whether this changes with redshift or not. So for this talk, in the interest of time, I'll be focusing mostly on the ionized gas, while the warm molecular and cold molecular gas is something which is under progress and will be a topic of a future research. So now let's come to the galaxy that we should target for outflow studies. So if you look at the star formation rate and black hole growth rate in the universe, this is the curve that we obtain. So the black curve here shows the star formation growth. All the other curves, including this red one here, shows the black hole growth rate. So the obvious thing that we can see here is that, okay, both of these grow up to, say, this point, which we call as the cosmic noon, because of this obvious shape. So the black hole growth activity and the star formation activity is maximum in the universe at a redshift of 2 or so. And so it is believed that during this epoch, and there was a widespread amount of black holes which were growing, the radiation from the accretion disk of the black hole dominated the feedback process. And as a result of this, there were loads of radiatively pressure-driven outflows that ultimately caused the shutdown of the star formation, as well as the black hole growth itself. So this epoch will be ideal to test radiative feedback from black holes. But we know one thing for sure. In order to get better resolution, you have low redshift galaxies. So what I will do is I will kind of keep going back and forth between the low redshift universe and the high redshift universe, because the advantage that we have with low redshift is that we can see the physics in detail. And we can learn, either we can learn or we can apply this technique for the high redshift galaxies. Okay, so now let's come to the sample that we actually used for our study. So we selected our sample from Super Survey. The Super Survey consists of X-ray selected AGN at redshift of 2. The X-ray selection ensures that there is no contamination from known AGN sources in these galaxies. So the plot over here shows the distribution of different surveys in the bolometric luminosity versus the redshift space. And you can see that in the red here is what is shown the Super Survey location in these parameter space against the backdrop of many other extragalactic surveys that are happening. The takeaway from this particular plot is that the Super Survey targets have a large range in bolometric luminosity compared to a lot of other surveys. So we will be least biased while searching for outflows. For example, if we only focused on the high luminosity targets, maybe we found outflows everywhere and we will not gain any information about the general AGN population. And the targets in the super survey have ancillary data in other wavebands that has allowed us to do SED fitting. Two of the examples are shown over here. And we were able to find many black hole as well as host galaxy properties such as the black hole mass, bolometric luminosity, star formation rate, stellar mass, X-ray column density, and so on and so forth. So the idea here was quite simple. We have a very good sample right now with a good characterization of host galaxy as well as the black hole properties. We would like to follow up these targets using AO observations, AO integral field observations to spatially resolve O3 emission and H-alpha emission. The O3 emission is tracing the ionized gas, while the H-alpha emission is tracing the star formation. So we would like to spatially resolve these in order to gain insights into whether the outflows, or rather whether the star formation is actively avoiding regions with high velocities or not. So here's an example of an integrated spectrum that we obtained from SINFONI observations. So the spectrum here shows very strong O3 emission, which is like these two emission lines. I just hope that you can see my cursor. And then there's a strong H-beta emission feature as well. So one of the first things that I said that what we want to do is that we want to find the velocity of the ionized gas in these galaxies. How do we find the velocities? We find them by measuring the width of the O3 line, which is primarily tracing this ionized gas. So we model these O3 lines or other emission lines using multiple Gaussian functions. And the right panel here shows the distribution of the velocity in the for the super surveys and other star forming surveys. So in the blue here, you can see the distribution of ionized gas velocities in star forming galaxies, which barely goes beyond about 600 kilometers per second. In red, which is the super survey, you can see that the ionized gas velocities are primarily greater than 600 kilometers per second or so. And as a consequence of this, we are setting the 600 kilometers as like the cutoff between AGN-driven outflow scenario and a star formation outflow driven scenario. So from this plot, it does look like the AGN increases some turbulence in these host galaxies, due to which we see higher ionized gas velocities in these host galaxies. So that was the case of integrated spectra that we just talked about. Let's have a look at a low redshift galaxy. So in the top panels here, we show spatially resolved BPT diagrams. Now, BPT diagrams is a way to find out whether the observed line ratios in a spectrum, such as O3, H beta, N2, H alpha, and so on and so forth, is it a result of ionization by AGN or star formation? So in this plot here, any data point on this side of the plot, the ones shown in red, is ionized by AGN. The ones ionized by star formation is shown in blue, and the ones ionized by composite processes are shown in orange or yellow, whichever color that is. This is the BPT diagram of the spectra obtained from individual pixels, which is shown here. And what we then do is we make the ionized gas velocity distribution, which is the O3 width distribution, for AGN ionized pixels and star forming ionized pixels separately. So it's quite amazing to see here that the AGN ionized pixels tend to show, on average, larger ionized gas velocities or larger O3 width compared to star forming ionized pixels. So this is quite incredible to see that what we saw at high redshift for an integrated spectra is kind of reconciled well with what we see in these low redshift at pixel or individual cloud scales. So as I mentioned earlier, that we are actually interested in spatially resolved emission. High redshift galaxies are extremely notorious in this sense because they seem extended, but then actually it might be just smearing because of the PSF emission. So let's focus on this particular set of plots. So I extracted emission from a target from this central location, which is shown in black here. And I also extract the spectra 5 pixels down, shown by this red square here, and it's shown by this red curve here. Now, when you look at it, look at these two curves together, the red and the black ones, the immediate thing that we see is that they're almost the same. The only difference between these two is that there is an overall scaling factor between these two. So what is this telling me? this is telling me that the spectrum is red in this location is exactly the same as what is at the central location. So it's mimicking the PSF in a way. So what we need to do is that we need to remove this emission in order to see whether there is a structure beyond the PSF that we can see. So what we did was we subtracted the central nuclear spectrum, allowing for the variation in the overall scaling factor. And if we see a noisy map, if we just collapse the channel, say here, and if we just see a noisy map, that means the emission is unresolved. But if we end up seeing such non-zero emission features, such as the one shown in yellow over here, then we can confirm for sure that this emission is resolved, and which you can also confirm via extracting the spectra, the species of subtracted spectra at that location. So once you're convinced that the emission is resolved, you can go ahead and make these velocity maps, and which for these two galaxies, for example, you can see that the velocities can reach as high as 1,000 to about 2,000 kilometers per second. And if you have these velocity maps for multiple emission lines like O3, H alpha, and so on and so forth, you can also estimate the inclination of the host galaxy with respect to these outflows. So in order to find out how efficiently these outflows couple with the ISM, or what exactly is driving these outflows, we try to find correlations between the outflow properties such as the velocity, mass alpha rate, with the AGN luminosity and other properties such as star formation rate and stellar mass. So the bottom line here is that what we find is that the outflow properties, so in this case we are looking at WAT, which is the outflow velocity here, and the m dot, which is the mass alpha rate, they correlate with the AGN luminosity no matter what. So again, similar to what I showed earlier, where I switched between the low redshift and high redshift survey between the pixel scales and the integrated scales, what we did was we looked at MUSE observations of low redshift galaxies and placed pseudo slits or pseudo fibers and calculated the properties again to find out whether the scaling relations that we are observing, is it a result of the observation technique that we are using? That means, are we biased towards just slit-dominated observations or fiber-dominated observations? So our result was, first, scaling relations do exist no matter what, so which is shown over here. So if you take, say, a slit spectroscopy or fiber spectroscopy, you do end up with scaling relations at a similar area of the parameter space that is shown here. And in the red, which is shown as the spatially resolved mass alpha rate, which also shows a nice correlation. Second interesting fact is that statistically, correlations are stronger if we extract the spectra at the center. So if I was extracting the spectra from, say, 3 arcsecond aperture, and if I was extracting the spectra from, say, 6 arcsecond aperture, my correlations are stronger if I was extracting the 3 arcsecond aperture spectra. So what this tells us that the outflow coupling with the ISM is strongest when you're close to the AGN location, which may not be surprising at the end of the day, but at least we have a quantitative estimate of this happening. So moving on, outflows by themselves are not that interesting. Thanks. So the outflows by themselves are not that interesting if they don't really do anything to the host galaxy, right? We want to know whether the outflows are actually affecting the star formation or the molecular gas content in these galaxies. So these are some compiled literature results where the background images show here the H alpha emission, tracing star formation, and the white contours here, the white ones here, and the black contours here, they all show the outflow locations. So the first look at this slide basically tells you that star-forming regions actively avoid regions with high velocity ionized outflows. So what you might say from this plot is that, okay, maybe I've already found negative feedback in action over here. And also, if you look at this particular galaxy, at the edges of the outflow contours, you can also see the enhancement of star formation. So maybe for this galaxy as well, there's a positive as well as negative feedback. When I say negative feedback, I basically mean that the outflow is removing star formation from the host galaxy. So maybe those kind of processes are happening simultaneously in these systems. However, do we really see this quenching in action? So the reason I bring this up is because there are conflicting results in the literature of the same target. So if you remember from my previous slide here, I showed you this particular diagram. Now, if you use AO observations or completely different observations, you end up getting this kind of a curve. which means that we don't actually see quenching in action in this particular galaxy. So for the same target, you're getting completely different results. In one case, you see a negative feedback in action, and in another case, you basically see that there is no feedback in action whatsoever. So I would just briefly give you why this may be the case. Is because, so if you look at these three graphs in this slide, the data is, the spectrum is exactly the same, but the H-alpha modeling is different depending on which assumptions you invoke. So the vertical blue lines here show the location of H-alpha and N2 lines. So the complication that happens in type 1 AGNs is that you have blending from different emission line components. And once you blend, you need to start modeling the lines. And the modeling depends on what kind of assumptions you invoke as well. So in this case, for example, you only fit with H-alpha line. But then here, you fit with both N2 lines as well as outflowing components and so on and so forth. So depending on what kind of model you have used, you may end up getting different results as I showed in the previous plot. And of course, beam smearing effects play a major role. So if you remember this beam smearing impact, and if you remove the PSF, so this is the comparison that I have from an image where the PSF subtraction was not performed and an image where the PSF subtraction was performed. So you clearly see that the H-alpha morphology in both of these cases are completely different. And it sort of mimics what we see over here as well. So there is a possibility that maybe PSF subtraction might be key towards finding out whether the star-forming regions are actually avoiding regions with high velocity ionized outflows or not. So this is what we find for one of the super galaxies. So this is a work under soon to be submitted, where we find the impact on star formation to be quite clear once we do the PSF subtraction. So this is the direction of the ionized outflow, and we can see that there is an enhancement, or rather there is more star formation taking place on one side of this. I should mention a caveat here that we are looking at unobscured star formation with H-alpha. There could be dust obscuration effect. The fact that we are only using AO observations where we are only sensitive to 2 kiloparsec, maybe there's a possibility that there is star formation happening right in the center and we are just not sensitive to it. So dust obscuration and high resolution observation will form a part of the future observations, or rather future work. So this is where I would like to conclude, where the future work will basically trace not just ionized outflows, but outflows in other phases using ALMA and JWST. We'll also be tracing AGN at very low luminosities. And star formation, we've only used H-alpha as a tracer here, but then there are many other traces of star formation. And thanks to JWST, we will be able to do a very similar analysis using mid-infrared data at redshift of 2. So I would like to leave you with my conclusions, and I'll be happy to take any questions that you may have. Thank you.
Thank you very much, Darshan. That was a very interesting talk. I don't know if people have questions. We have probably time for 1 or 2 questions. If you do have a question, please use the raise hand button at the bottom of the people tab, or write your question in the chat.
I can ask a very quick question. Darshan, thank you for the talk. It was really, really interesting. So as you mentioned with MIRI, with Webb, you're going to be able to access the warm molecular gas. I guess in the mid-infrared, you can also study some of the ionized gas. Do you have any targets, or, obviously cycle 2 is coming fast, that you would like to target with Webb specifically?
So we do have cycle 1 approved for some of these targets that I showed today. So we will be tracing warm molecular gas for a subset of these galaxies.
Do you have, I assume maybe you have like complementary molecular gas observations for the cold side?
Exactly. Yeah. So the ALMA observation, so for all of those targets that have been approved, I think we have both ALMA observations as well as SINFONI observations of ionized gas. So I think it's the warm molecular gas, which is the only one which is left.
There was one question in the chat. But Ian has his hand raised, so I'm going to call on Ian first.
Oh, hi. Yeah, thanks for the great talk, Darshan. I was just wondering regarding the beam smearing effects, given that, as you just demonstrated, it can lead to completely different or very different star formation profiles. Do you have a quantitative idea of all the studies, or at least most of the studies that have been done, which have not taken the beam smearing effects into consideration? How different would this particular results be if they had taken that into consideration? Like, is sort of like a redo of those studies have been done or not?
Yes, there have been attempts to redo some of those studies. Unfortunately, I don't really have a literature compilation of those because we primarily looked at the targets from this survey, and that's how we got to know that, okay, maybe we do need to take this into account. So yeah, I think it's an interesting question, and it is something that needs to be pursued, that if there are literature results related to the star formation versus the outflow location discrepancy, then yeah, we might need to revisit them, redo the analysis, which was, I think, was done for ionized outflow perspective, but not for star formation back in 2016 or so. So yeah, I don't have an idea about the literature, what they have done, or rather how many studies might be affected by that. But then yeah, it's something worth looking at for sure.
Okay, thanks.
In the interest of time, I think we have to move on. Darshan, there's one question in the chat from Mireia. Maybe you can just answer that also in the chat. Thank you so much for your talk. The second speaker that we have today is Petia Yanchulova. She got her PhD at UC San Diego in 2020 and based her thesis on HST data of the small Magellanic Cloud to learn how dust, stars, and galactic structure in tandem produce the observed dust extinction and stellar properties of the SMC. She has been a postdoctoral scholar at Space Telescope since 2020, working primarily on studying interstellar dust extinction in nearby galaxies with people in the ISM Stars research group. Today, she will tell us about the SMC stellar dust and 3D geometry properties from resolved stars. Petia, please take it away.
Thank you, Ramona. I will share my screen and let me know how things look on your end. You can see that. Okay. You can see now just my title slide. Good. Well, a big thank you for having me, and thank you to the organizers for putting this series together. I am a postdoctoral scholar here at the Institute, and the work I will talk about today was done alongside Carl Gordon here at the Institute, Karen Sandstrom, my thesis advisor at UC San Diego, Claire Murray, and other folks here in the ISM Stars research group. Today I will share with you what we have learned about interstellar dust extinction and 3D structure of the nearby dwarf Milky Way satellite, the Small Magellanic Cloud, through observations done by the magnificent Hubble Space Telescope. So here is a zoomed-in beautiful HST image of the N13 nebula in the Small Magellanic Cloud observed as a part of the SMIDGE survey. All of SMIDGE, including this nebula, was observed in 9 wavelengths from the near infrared through optical to the near UV. And this particular image here is a composite of 3 wavelengths, which together allow us to see the fascinating properties of the observations. Immediately, we see a lot of individually resolved stars at different colors and brightnesses. I will briefly show the images at these different wavelengths, ranging from the near UV to the near infrared, so that we can begin to appreciate the richness of Hubble's power to reveal different features at these different wavelengths. We can see that some of the stars are visible at all wavelengths, while others are not. We see a bright central star emitting strongly in each band, and in its vicinity we see the gas, hydrogen, glowing due to the heating from this intense UV radiation. Stars are born in this nebula. In all the images, you will notice the patches of dust and gas, which appear quite dense and significant at some wavelengths, and not so much at others, and as such affect the light from the stars embedded within the dust or that are behind it. We call the dust and the stars, which are among the stars, the interstellar medium, or ISM for short, In the combined image on the lower right, we can see that some of the stars are dimmer and redder, and this is mostly the doing of dust, that it changes the color and brightness of stars as we perceive them. I will share how my work relies precisely on this information encoded in these beautiful color images and color and brightnesses to understand intrinsic stellar and dust properties. So my work specifically focuses on understanding dust extinction in the SMC as measured from this interaction of dust with the hundreds of thousands of individually resolved stars. And also I will talk about how dust extinction may relate to the ISM environment. So as a summary for the motivation of my work, I've already answered the first two questions. Going to number 3, we want to apply a robust method systematically to a representative number of sightlines towards all of these stars, whether they're red, blue, bright, or dim, across a variety of environments with different amounts and types of interstellar gas and dust. I mentioned that we can answer these questions with photometric data sets of resolved stellar populations. And hopefully one very useful product from our work is high-quality catalogs of stellar and dust properties for a great many stars of different types, so that people can go and look these up along a sightline and use these catalogs for any targeted studies they may wish to make to answer additional science questions. So here are the large and the small Magellanic clouds visible from the southern hemisphere. Specifically, the SMIDGE SMC survey hosting the brilliant N13 nebula that you saw is in the lower right of this image, in the center. And that is the region with an appreciable amount of dust, different stellar populations, and ongoing star formation. And here you can see the survey footprint. First, I'll have to take you through a brief, basic description of how we quantify dust extinction. So the main tool is the extinction curve, which is the function defining the extinction of light at a certain wavelength. Extinction is characterized as the effects of absorption and scattering. And to understand what dust is, we may ask, what materials may be present in the interstellar medium to produce the observed extinction of light? Or what may be causing this particular shape of the dust extinction curve at these particular wavelengths? At a minimum, we know that dust is composed of small solid grains, predominantly silicates and carbonates. The traditional way to measure dust extinction has been to use a pair of stars of the same spectral type, where one is reddened and one is unreddened, and compare their spectra or their flux per wavelength. Dust extinction is thus measured in magnitudes, which at a basic level depends on the ratio of the fluxes of the unreddened and the reddened star. You will notice 3 main features of the extinction curve. There's a general rise from the infrared, which is on the lower left or on the left of the plot, to the ultraviolet. Extinction tends to go to 0 as the wavelength increases to infinity, down in the lower left, and there is a prominent bump at 2175 angstrom, plus there are other spectral features if we were to zoom into different parts of the spectrum. So dust extinction curve within the Milky Way are observed to vary. This variation is due to the interstellar environment or the material through which light passes. To quantify this variation, we can use a dimensionless parameter called RV, which describes the slope of the extinction curve at visible wavelengths. And thus it is the ratio of the extinctions at these 2 wavelengths. Sightline through the diffuse Milky Way ISM, which contains a large fraction of smaller grains, have an RV of 3.1. And sightlines through dense regions, which have a larger fraction of large grains, tend to have larger values of RV. Smaller grains are better at blocking light at shorter wavelengths. This is why you see the blue extinction curve having lower RV. And since most of the surface area of the dust is in the smaller grains, but most of the mass is in the larger grains. A changing RV speaks about the evolution of dust, since when dust grows through coagulation or accretion, some of the smaller grains are used to form larger grains. And here I'd like to refer you to recent Discovery Series talks by my colleagues, Chris Clark, Marjorie de Clare, and Dries van de Putte, if you'd like to learn about some of the details about dust evolution, dust extinction in the Milky Way, or the far UV dust extinction, all of which we have kind of summarized in this slide here. So basic differences in the extinction curves within the Milky Way exist. And these are, there are marked differences between extinction curves in other galaxies, such as, for example, the small Magellanic Cloud. It's known that most sightlines in the Magellanic clouds do not follow the arc-dependent relationship generally seen in the diffuse Milky Way ISM. For example, here, in addition to the dark blue Milky Way diffuse ISM curve, I have plotted in light blue the SMC bar average extinction curve measured by with the UV spectroscopy by Gordon et al. 2003. And you can see right away that this curve has a steeper UV rise and lacks the 2175 angstrom bump. When we examine the Magellanic clouds, and in particular the SMC, we do see differences in the ISM environment. For example, the SMC is only at that's supposed to be 1/5 solar metallicity, not 1.5 solar metallicity. Sorry, there's a typo. And so the environment is quite depleted in heavy elements there. Thus, we would like to characterize these different types of extinction curves. The way we can do this is to introduce a mixture parameter, FA, to describe the mixture model relationship. So is there a systematic variation of extinction curves with metallicity? We can take a look here at how keeping if we have two potential input RV curves, values, then if we keep the RA constant at Milky Way 3.1 but vary FA, we can see how the actual output extinction curve varies simply by varying FA. And so, so how can we represent all these observations in a way which would allow us to exploit the richness of the multiband HST photometry and study dust extinction, the 3D geometry and stellar properties? One way is to plot all the observed stars on a diagram, which in a sense is very simple yet holds a vast amount of information. Some of you may be more familiar with the HR diagram in astronomy, showing the temperature versus luminosity for a set of stars, where each star has a specific temperature and luminosity. The color magnitude diagram, or the CMD, is a close relative showing the stellar brightnesses on the y-axis and a version of the stellar color on the x-axis. We would like to study the effect of dust and galactic geometry on the sets of stars or stellar populations on the CMD. Here's a brief illustration on the far left with a theoretical synthetic CMD specifically generated based on known properties for the SMC smidge region. The main sequence is the diagonal feature, which hydrogen burning stars of various masses occupy on the CMD. As a set of stars, much like our own sun, begin to run out of hydrogen, they leave or evolve off of the main sequence in an almost vertical sequence called the red giant branch. And then for quite some time, these stars sit in a tight spot called the red clump in magenta. Without dust, the red giant branch or the RGB is a narrow feature, and the red clump is a compact blob, as you can see in the zoomed in middle plot of the same color magnitude diagram. If we simulate the effects of dust on the synthetic CMD applied as the distribution of extinctions to the stars, then on the far right, we'll see that the red clump is extended in color and magnitude, and the red giant branch actually appears also extended. And as a matter of fact, here it almost appears double. But keep in mind that the middle and the far right plot have the same numbers of stars, with or without dust. All CMD features are affected by dust, including the main sequence, but it is harder to see the effect there due to the orientation. We thus pick the most prominent feature, the red clump and the RGB, to study dust extinction. Here are the smidge color magnitude diagrams in the 8 photometric bands varied on the y-axis, plotted in a constant color of optical color, which is a difference of 2 bands on the x-axis. The same set of stars are shown in all panels, only they appear differently at different wavelengths, a bit like those initial images which I showed you. The effect of dust extinction on the stars varies correspondingly in each CMD, and this variation can be measured. Here in the toy model on the lower right, you can see the effect on the stars behind the dust, which are displaced in both color and magnitude. So they're shifted vertically and diagonally in these panels. Our approach, therefore, is to measure the slope of this red clump in the CMD of each band, and in this sense, we're in effect measuring the extinction per wavelength, or if you remember, that would be the slope of the extinction curve, or RV. So here, for each individual measurement, we get a result, which is a resulting point on the dust extinction curve in the middle panel. The result of this average curve for the smidge region is shown here, we find that it's generally consistent with the one from UV spectroscopy by Gordon 2003. Interestingly, however, we find an unexpected offset from that curve. We test this method in the 30 Dorados region of the LMC, and we confirm the results of another group which also finds an offset there. When we think about what could be causing this offset, we realize that the SMC has a huge depth along the line of sight. So in addition to extinction by dust, stars on a CMD can also move vertically due to being fainter or brighter or farther away or closer. So we used the red clump toy model that I showed you to simulate galactic depth and dust extinction, and stars behind the dust are indeed farther away than expected, and those in front are closer. So this makes them appear fainter where the magnitude increases. And the effect is an actual steepening of the reddening vector slope. Thus, an important conclusion from our work is that the line of sight depth needs to be considered when we use stars as a background to map the dust. Now, going a step further with the color magnitude diagrams, we took the approach to actually fit this red clump and red giant branch region to make a more sophisticated model where we know some star formation history, meaning we know the locations and color magnitude of the stars, the unreddened stars, and here we simulate the data where we vary the dust extinction distribution, we vary the depth of the star, of the galaxy along the line of sight, and we also vary the relative position of the stars and the dust. So we experiment, we put the dust in front of the stars, behind the stars, and we actually, it turns out, once we use this method where we sample a grid of parameter ranges and we account for the line of sight depth, we find that there are, there is a confirmed significant line of sight depth, and also we find that the dust is on the near side of the stars. Something interesting that you can actually see in this color magnitude diagram is that this doubling of the red giant branch is due to the fact that the dust is assumed to be in a thin layer relative to the stars, and so we don't think that there are any stars embedded within the dust. If there were, we would see differential extinction, and so there would not be this gap. But here we see clearly an unreddened and a reddened red giant branch, so clearly stars in front of and behind the dust. And so what is the result? Finally, we have used these resolved stars to constrain the structure of the SMC and the dust extinction. It's a very powerful method, and we have to keep in mind that in the Magellanic clouds, we have to account for the 3D structure of the galaxy when we use stars as a background to map the dust. The value of this method is that it can independently estimate AV, which in effect can be compared to AV calculated from infrared dust emission, which uses the dust grain model. And so in a sense, dust grain models can be calibrated with an independent method. But there are limitations to this model. We only were able to use about 12,000 red clump stars and red giant branch stars that measured only the average properties. So how can we build onto this work? We can systematically derive dust and stellar properties for all of the stars in the smidge region and for all of the stellar populations, not just for the red clump and the RGB, so that we have a representative picture. And our goal is to produce high quality catalogs which other people can use that list dust and stellar properties and also make relationships with interstellar environment. So the way we do this is we use the BEAST tool, which is spectral energy distribution modeling tool using the Bayesian framework. The BEAST recovers the intrinsic properties of individual stars and dust along the line of sight. It is designed for large photometric surveys, but it can be used for individual stars. It accounts for the dust extinction in a robust way, and also it accounts for observational uncertainties, which are always inherent in large surveys. The computation of a BEAST model SED for a dust extinguished star is shown graphically here on the right. The top panel gives the stellar spectrum, the unextinguished stellar spectrum. The middle panel shows the extinction by dust on this spectrum, and the bottom panel plots the full extinguished stellar spectrum combined. The bottom panel shows the integrated SEDs for, here specifically from Gordon 2016, the FAT survey of M31 band passes, and they're plotted there along with their effective wavelengths. So this tool is open source, and anyone who wants to participate is welcome. Now, what do we see when we apply this tool to all the stars that you saw in the smidge region? And you actually saw only a small fraction of it in that N13 nebula. Well, here we are showing a sample of results. This actually includes the 1D PDFs for all the stars, where those are about a little over 500,000 sources. We see these distributions, and they seem reasonable. Besides having this result and a probability distribution function for each parameter, for each individual star, here we have just shown the mean of the actual P50 values, which is the median of the whole sample. So we obtain a catalog of results of stellar and dust parameters. Here on the left, the 3 plots are the dust parameters. On the right are some of the stellar parameters, not all of them. And again, we'd plan to make this catalog available. But going on with examining how those dust parameters may be correlated with the inner environment, as we wanted to explore early on, we compare here in this map of AV. So this is the full smidge region, more than 500,000 stars. This map of AV values we compare to various ISM tracers such as neutral hydrogen, dust mass surface density, carbon monoxide, and we see the clearest correlation between the dust extinction and the CO intensity. And here I've plotted the CO intensity contours on top of the left-hand plot. So CO traces cold, dense, in the cold, dense interstellar medium. Now these are very, very valuable because this is the highest spatial resolution ISM tracers that we have for the SMC, and it turns out to be an excellent tracer of the dense ISM. So we thus have 2 independent measurements which appear to be correlated, one from photometric measurements and another from CO gas measurements. They knew nothing about each other before we made this comparison. And so higher AV traces denser molecular clouds. We also compare to H1 and the dust surface density, but this is the best correlation that we find. We do these comparisons for the other dust parameters like RV, which describes the extinction curve slope, as you know, and FA, which is the dust mixture coefficient. And we may see some correlations, but they're smaller. Particularly, we may see some correlations in higher CO intensity regions, so denser molecular clouds. And it may make sense because in denser molecular clouds, the grains may tend to coagulate or accrete, and that therefore increasing RV and perhaps increasing FA. High values of FA would indicate more Milky Way type dust. And so whether they're correlated or not, there are various explanations for that, but we need to explore this further. Another potential use and for our study and for using the BEAST tool is, first of all, if we compare how the BEAST matches up to, say, the literature, spectral typing and temperatures derived from those spectral types, and the BEAST derived temperatures. Here we have a comparison where on the y-axis we have 12 stars. There are 11 stars from Maisa Pelani's and Rubio 2012. And on the x-axis is the temperature from the BEAST-derived smidge temperature. We see a very good correlation. One thing that was very valuable from smidge is to use this tool for directed studies where we can target specific stars which may show the probability of a bump or not in dense molecular clouds. And so I will finish here, where my conclusions are that we've created high-quality catalogs of dust and stellar properties of many stars and many stellar populations. We have derived all these parameters for each individual star. We have high-quality maps of dust extinction properties across the SMC, or in the smidge region in the SMC, and we have some first impressions about the correlations between AV and CO as an ISM tracer. And some future work is to examine existing and upcoming
Oh, Petia?
I think everyone in STScI has lost the connection.
Okay, so sorry guys, we are having a connection problem. Oh, you're muted, Petia.
I can hear you now.
Okay, perfect.
Yeah.
Okay, sorry all for the interruption. Hope everyone's more or less back.
Yeah.
I don't
Okay.
know where you stopped hearing me, but I hope you saw my conclusions.
You did see your
Slide
conclusion.
after that.
I
Okay,
think
good.
I think you dropped out like maybe halfway through that slide.
Okay.
Yeah, thanks so much for your talk, Petia. Sorry for the interruption at the end. We do still have time for one or two questions, so if you have a question, please raise your hand or write it in the chat. Francie.
Great talk. I was curious because I think you were starting to explain a little bit about it before it went out, but on your conclusion slide, you talked about the forthcoming catalog with distance revisions. And I was wondering if you could say a little more about types of stars that would be included in that catalog, or just a little more about the distance estimates and errors within for those stars.
Yeah, so we plan to, well, right now, currently, I do have distance estimates for all those stars. I just haven't shown those results. I had a very coarse grid, but I will refine my grid. So what we're planning to do with the Beast is to actually build into it, in a version of it called the Mega Beast, an estimate of the completeness of the observations, because you have to know to what level you are complete in your photometry to be able to say whether you're seeing all the stars. And so we're planning to, you wanted me to answer questions about the uncertainties and the types of stellar population. So we are fitting all the stars that we see. We're working on developing models for some stars which we don't necessarily have existing models for. Like, we're working with binaries into the code, and that's of course very important. And so the uncertainties, we'll be able to see substructures. Like, we hope to be able to see substructures within the SMC. So like we may be able to see at what point where the dust clouds are located within the galaxy, where the stars are, etc. So those are a few kiloparsec scales that we hope to be able to.
Right. Do we have any final question? If not, thanks again very much, Petia, and also Darshan. The email addresses of both Petia and Darshan are in the program, so if you want to reach out to them with further questions or anything, please feel free to do so. Thank you all for joining today, and see you next time.
Thanks for having us. Bye.